All right, hello folks. Welcome to EfficientML.ai lecture 6, where we'll dive deeper into quantization, the second lecture for quantization. So lab 1 was out. Make sure you downloaded it. Last week, we updated our labs group website, which is hanlab.mit.edu. And unfortunately, that disrupted one of the links of the PTH file in our homework 1. So yesterday, the TAs has posted on Slack the fix for that. So our original website can still be accessed by hanlab18.mit.edu, while our new website is hanlab.mit.edu. So if you haven't downloaded the homework lab 1 yet, you can download the new one. If you have already downloaded but cannot download one of the files, you can just follow the discussion in the check your email. So we have a fix for that. And try to be nice, we accommodate that by giving you extra 2 days to finish the homework, although we just took a few hours to fix that, but we want to be lenient and give you two more extra days. Hopefully that doesn't cause too much distraction. If you have any questions about lab 1, feel free to ping us. We have office hour every Thursday after the class. Okay. So in today's lecture, we'll first review the linear quantization, which we talked about in the previous lecture, followed by 2 very important techniques, very widely used in industry in practice, which is post-training quantization, just recover the accuracy after training and without any fine-tuning, which is very computationally efficient. Sometimes PTQ, the post-training quantization, cannot fully recover the accuracy after quantization. Therefore, we are going to introduce the QAT, the quantization-aware training technique that can recover the accuracy by fine-tuning the model. Following that, we are going to go more aggressively and dive deeper into binary and ternary quantization. And if we have time, we'll talk about mixed precision quantization to give different precision for different layers. So this is our agenda. In the last lecture, we talked about this floating point weight, floating point arithmetic, which is basically before quantization, versus the k-mean space of quantization, which can save the storage. Okay, so here we are using quantized weight, but arithmetic is still floating point. This is still quite useful. We're going to see that in our lab 2 and also our Llama 2 deployment on the laptop. Since the large language model is purely memory bounded, computation is cheap, memory is expensive. This method can be super effective by compressing these large language models. We're going to revisit this during our large language model lecture. Also, we introduced linear quantization for both the weight and also the activations. So the arithmetic and also the storage are both using lower precision. So reviewing the k-means quantization, floating point weight, we cluster them by sharing the grouping for similar weights. And we only need to store this low precision index plus the codebook. The codebook is usually much smaller than the weight dimension. Imagine you have only 4 bits, so the codebook has only 16 entries compared with 1,000 by 1,000 dimension in the weight itself. We further show that pruning and quantization can work together to further boost the compression ratio further to the left-hand side, make the model much smaller while preserving the accuracy. We further described in last lecture about the affine mapping for linear quantization. So this is the original weight. We introduced this 0 point, which maps the quantized weight 0 point to be 0, and the 32-bit floating point number, which is the scaling factor. So the scaling factor basically map the range between Q mean and Q max, which is the quantized mean and quantized max, to the real number, to the actual mean and max of either the weight or the activation. So for different bit width, remember we have a fixed set of qmin and qmax. If we have 2 bits, qmin is -1 positive, -2 positive 1. And if the bit width is 4 bits, you can correspondingly find the qmin, qmax -8 to +7. Further, we had this long derivation, which we're going to see in lab 2. So make sure you master this technique pretty well. Assume the weight is symmetric, bias is symmetric, so z are 0. Okay, and we define sp to be this term, and define q bias to be this term. So we can finally get this equation. And so qw times qx, the quantized weight, matrix multiplied with the quantized activation, plus the bias, and rescale it and added with the integer add. Okay, so here for QB and Q bias, since the bias is having a lot smaller dimension, okay, compared with the weight, so we can afford it to use 32-bit to store it, and to prevent overfitting the accumulation in the matrix multiplication are also done in 32-bit integer add. Similarly, for convolution, we just replace the matrix multiplication with conv, and the rest of this formula looks pretty much the same. So we'll give you a hands-on tutorial to walk you through this step by step in our lab 2, which is going to come soon. All right, so let's talk about post-training quantization and some details. Okay, we start with about quantization granularity, followed by the dynamic range clipping. So similar to pruning, we also want to find a proper granularity of quantizing either weight or the activation. And lastly, the rounding. So let's start with the quantization granularity. Just like pruning, remember during pruning, we had a full spectrum of pruning granularities. Remember what are those granularities for pruning a CNN? Remember, we had a full spectrum from here to here, most fine grained, most coarse grained, right? So similar to pruning, quantization also we can have different granularities. We can quantize the whole tensor. In the full tensor, quantize it using the same scaling factor, the same 0 point, or we can have finer granularity, like quantize each channel independently. They can have different range, different scaling factor, different 0 point, or we can be even more fine-grained. Okay? Just quantize a group of values, either per vector, or we can even share some of the exponents across different numbers. So this is the recent very popular MX, MX4, MX9, etc. We can introduce that. So you can imagine which one is more hardware friendly and which one is likely to give higher accuracy.
The one on the bottom is more accurate, and then it goes up into less accuracy.
Right. This one is more likely to achieve higher accuracy because you have finer granularity. You can afford to have more detailed scaling factor for each subvector, right? Well, this one is more coarse-grained, so it's probably less accurate, but more hardware friendly since it's more regular. You just apply one scaling factor to the whole tensor, and probably more storage efficient since each subvector you need a scaling factor, a bias. But here you just need a single scaling factor and a single bias. Okay, so let's dive deeper, starting with this per tensor quantization. So in per tensor quantization, the Rmax is basically the whole tensor's absolute values max of the absolute value. Okay, so it samples from the entire tensor. You plot the distribution, you get the absolute value of each element, and you find the largest one. But as we have many different channels, say in a CNN, just plot the range of different channels. Okay, so like here we have 32 channels. actually different channel. What do you observe here about their range? It's quite different, right? Different channel are quite different. Some of them could be pretty small versus pretty big. Some of them stay within this tiny little range, not much difference. Okay, so it's pretty unfair to use just a single scaling factor, a single bias, a single max value to capture each channel. Okay, therefore, using a single scaling factor for the whole tensor sometimes drops encourage accuracy drop, especially for small models. Okay, so there can be pretty large difference in the range of weight. It's at the big range, it's at the small range, and sometimes you have outlier weights. So the solution is to use per channel quantization. Treat them independently. Each one has their own preferred scaling factor. So that motivated our second scheme, which is per channel quantization. Give a slightly finer granularity. And let's see the example to fortify our knowledge. So 2-bit linear quantization with our familiar example 4x4 matrix. If we are using per channel, if we're using the per tensor quantization on the right-hand side, this is what we learned in the last lecture. So we just find the absolute value of each element and find the max of them. And which one is that? 2.12. Okay, that's the R max. The max value across the entire tensor. And then remember, how did we calculate the scaling factor? So Q max, here we have how many bits? 2 bits. Okay, therefore, the Q max is ranging from -2 to +1. Okay, so we can divide R max over the Q max. Q max is determined by the number of bits. So the scaling factor is 2.12. Okay, so we use this scaling factor. We can get the quantized value. And then we multiply that since it's metric, there's no bias. We multiply by 2.12, we can get this reconstructed weight. Okay, and if we see the difference between the original W versus the quantized W times the scaling factor, which is the final value, is 2.28. And we do better using per channel quantization. So what are we going to do? How are we going to change the S?
Do the R max for each row?
Yes, do R max for each row. You have your private scaling factor and R max. Right? So we do it for the first row, this one, right? 2.09, that's the largest. Second row, even bigger. R max S1. Third row, R max S2. Okay? They are all different. You have your private scaling factor. Fourth row, this is R max, okay, R max, and the scaling factor. And we are going to use this private scaling factor to quantize each channel independently. So we get this quantized value, and also the reconstructed weight matrix. And as you can see, they are using different scaling factors: 2.09, 2.12, 1.92, and so on. And what is the new reconstruction error? The difference is 2.08. It's indeed smaller than the original reconstruction error, which was 2.08 or 2.28. So what is the overhead here? Is that free lunch? Let's use per channel always.
You're storing a lot more information.
Right. You have to store more information. Now you have to store 4 scaling factors. Each one is actually pretty expensive. That's 32 bits. It's not cheap. Previously, we need only 1. And this is a simple example. Only have 4 channels. in large language models, you can easily have 10,000 channels. 10,000 channels, you have to store 10,000 32-bit floating point weight. That gets non-trivial. And you observe some difference between the quantized weight here and here. This one, this one. Some of you may saw this is -1. Okay, all the previous values are the same, but only this one is different. And what caused this subtle difference between the vector between this per channel versus per tensor quantization? So previously, this -1 corresponds to -1.03. During the per tensor quantization, the scaling factor is 2.12. So this number divided by 2.12, the absolute value is smaller than 0.5. Therefore, it's quantized to 0. Since it's smaller than 0.5, it's rounded to 0. But using per channel quantization, okay, this number is going to divided by what? 1.92. Okay? And it's large, the absolute value is larger than 0.5. Therefore, it's rounded. The absolute value is 1. Okay, and we can see the subtle difference. Obviously, this is probably better than just ignoring this number and treat it as 0, but we can treat it as -1. All right, so can we do even smaller, right? So this method is per channel quantization works super well for vision models. Like this is what we solved last year's lecture. We don't have this, we can just go home. Unfortunately, large language models came roughly November in the fall of last year, and then we experimented with the per channel quantization. Actually, find if you want to go to lower bit, that is not enough. If you want to go to 4-bit, we need to go even finer granularity by using even smaller group size. Even within the channel, we want to further divide it into like here 2 parts. We have sub vector, so we're going to introduce a vector quantization. And an even more complicated version by Microsoft, which is the MX data type, shared micro exponent MX data type. This is completely new for this year's lecture. So we are going to introduce one more scaling factor. Previously, we talked about each tensor, we have a scaling factor for each tensor. Now we want to have another scaling factor for each sub-vector. It may not be as big as a whole channel, like large language model channel could be 10,000, pretty big. So for every like 32, 16, or 128, sorry, 64, 32, 16, 128, those are the most commonly used vector size. We have a dedicated private scaling factor for each sub-vector, okay, which is forming this kind of hierarchical scaling factor. First hierarchy and second hierarchy. Okay, very coarse-grained scaling factor shared by the entire tensor versus finer-grained shared by this every group of 32 values. So since this gamma is shared, is very low overhead, you can amortize overhead. This could be a 32-bit or FP16 high precision coarse-grained scale factor. Well, this per vector, like every 16 elements, you don't want to have a super high precision. So this sometimes has lower precision. So that is usually always a balance between the accuracy and the efficiency, right? The finer granularity go, the higher the accuracy, but the more redundancy, the larger overhead. So let's calculate the memory overhead using an example. Given a 4-bit quantization, okay, with a 4-bit per vector scaling factor for every 16 elements. What is the effective bit width? 4-bit quantization width, so each element has 4 bits, okay? And every 16 elements, they share a 4-bit scaling factor. Every 16 elements, they share a 4-bit scaling factor. So each element equivalently has a quarter bits. So 4 plus a quarter, that's 4¼ bits. So that's the way to see the effective number of bits. So we can have a more general representation here with this multi-level scaling scheme. Okay, so this is an individual weight. We have this equation previously with a single scaling factor. Now we can have level 0, level 1, and so on, multi-level of scaling factors, where R is the real number value, Q is the quantized value, Z is a 0 point, mapping mapping Z to 0, and S is the scaling factor. Previously, we introduced this per channel quantization. Okay, so this per channel quantization, each data is into 4. The group size for the first level is like the entire channel share one P16 scaling factor. And there's no one scaling factor, just one single level. VS quant, okay, introduced another level, second level, which the first level is still this individual. So first level is basically every 16 elements is going to share the unsigned into 4 scaling factor. And then the entire channel is going to share another FP16 scaling factor. And so we have 2 levels of scaling factor. First level unsigned in 4 shared by every 16 elements. Okay, every 16 elements, 4, but imagine this is 16. And then FP16 scaling factor shared by the entire channel. So what is the effective bits per weight? Rather than 4, now we have 4 plus 4-bit scaling factor shared by 16 values. Did we miss something? Actually, we ignored this scaling factor, which is shared for the entire channel, which is 4,000, 10,000. So that's so small, so we just ignore it. And very recently, Microsoft proposed this MX data type. Okay, so it's slightly more complicated, still having 2 levels of scaling factor. The first level, actually the data type is S1 minus theta 4 minus theta 2. So depending on if it's MX4, MX6, or MX9. Okay, yeah, MX4, 1 sign bit, and you have 2 bit of Mantisa. Where's the exponent? The exponent is here. You have 1 bit of exponent shared by 2 values. So for MX9, you have 1 bit of exponent also shared by 2 values. And next, every 16 elements, you're going to have another 8 bits of exponent to increase the dynamic range. Every 16 elements, you have 8 bits of exponent to control and expand the dynamic range. So the difference between MX4, MX6, and MX9 is that it has different precision, different Mantisa bits. So remember in last lecture, we talked about FP16 and FP8, which is available in Transformer Engine in H100. Each number has their own exponent, but the difference here is that 2 elements share 1 exponent. And further, 16 elements share another high precision exponent. So why this is called MX9? You have 8 bits here, right? 1 sign bit and 8-bit Mantisa. You have 1 exponent bit shared by 2 values. So that effectively how much? How many? Half, right? And then you have 8 bits shared by 16 values. So effectively, you have another half. Half, 8. Altogether, you have 9. That's why it's called MX9 here. All right, this is getting popular representation in large language models, so I don't want to cover that number representation. And this could be a active research topic, like how to share, how to not to share, what is the hierarchy, what is going to be the precision for each hierarchy. That's a pretty large design space. I think if you want to find an open project, that could be one of the project idea to explore whether you can design your own data type that give a good trade-off between the accuracy and also the hardware efficiency, especially for modern large model workloads. Okay, now let's switch gear to the second part, which is clipping the dynamic range. We mentioned this dynamic range. Question here.
Last slide one for clarification. Would it be fair to say that the trade-offs across those different DSU, MX4, MX6, or I guess the MXs would be in the weights you want to represent? How much scale variation is there versus how much sort of precision variation is there at the same scale? Is that a fair description?
So you can see the exponent bits, 8 bits, they're all 1 bit, all 8 bit. So dynamic range is pretty much the same. Like here, the precision is different. The mantissa bit is the key difference.
So the mantissa would be the range in your weights. How much diversity is there at the same scale?
Right, exactly. Since the range matters a lot, how do we select the range, especially for activations? Weights are easy, right? Weight is static. No matter what input it is, the weight stays the same. But different images, they may have completely different data. So how do we find the range for the activations? So our first method is during training time. Okay, we can have this exponential moving average. We track the exponential moving average during training. For example, after every epoch, we check the Rmin and Rmax for this particular batch, and we run this combination of T-1 T to update the range of T, including both the mean and max. So this is smooth across thousands of training epochs. Scaling factor is alpha. So this is during training. We can also calculate this Rmin and Rmax at runtime. So we collect a calibration data set, which is separate from the training and the validation. So which is separate from the test data set. Okay, this calibration batch, we can calculate the mean and the max. For example, we can using the average of the mean and max. And we can also find the max of the max. We can also have smarter way to determine how to get the statistics from this calibration set. And one of the heuristic is assume. This is just assume if the activation follows Gaussian or Laplacian distribution, then we can have this closed form dynamic range to clip it. So first of all, the intuition is that if you clip too much, the larger weight, the larger activation will have a large quantization error. But if you don't clip here, you will have very sparsely scattered centroids. You're wasting the centroids, for example, here. Centroid here probably is more useful. So if you have a Laplacian distribution, you can have this closed form determination about where do you click. Depends on how many bits do we have. What if the distribution is non-Gaussian or non-Laplacian? A super widely used method, actually that's the method use the NVIDIA's TensorRT toolbox is using this KL divergence to find the best location to clip it. If you clip it here, if you clip too far to the left, you may have a large error for these activations. But if you clip here, you're wasting the centroids on these small distribution, these values, which has very small amount of percentage. Okay. So we want to optimize the location of the clipping by finding the by optimizing the KL divergence. One is before the clipping, one is after the clipping, P log P over Q. And the intuition is that this KL divergence measures the amount of information loss, okay, when approximating a potential given encoding. Okay, before clipping, we have a distribution. After encoding, we have another distribution. We want to make them similar and minimize the loss of information. And let's see what happens after clipping the ResNet 152, this particular layer. And we find the KL divergence determines to clip at here. So what happens to these two distributions? This is original distribution P. This is distribution Q. We see a point here. Why is this point here? All the points to the right of this clipping line and gets rounded to this value. Okay, and put them together, you have a pretty large number of them. So that's why we have abrupt change here. And KL divergence is basically trying to optimize P and Q to minimize the information loss. Here are more examples. What happens to clipping? I like that after putting layer 2, click here. This is Google Net. After clipping range is here. ResNet 152, click right here. This is pretty interesting distribution. Google Net, click right here. They are all different. So recently, NVIDIA proposed another approach to find the best clipping. Okay, so there's animation here. There's a trade-off. If actually, it's better to see from this animation where if the clip is the absolute value is too large, you have very big wasting your centroids on the distribution where actually not many numbers using this value. Okay, but if you are clicking too aggressively, these values in presentation will be inaccurate. So that's why if we plot the clipping scalar from the smallest one to the largest one. Okay, so now the smallest one, now it's the largest one. Okay. As you go from a large one to a small one, we can see the MIC, the mean square error, first a decrease. Why decrease first? When we are doing this, why the MIC first decrease? Because initially, if you click here, we are wasting a lot of centroid to these locations where actually not many weights or activations are choosing this value versus it's more useful to put them here. But later, as you clip too aggressively, the error is going to increase again. Because here, as you clip too aggressively, all these blue area will be clipped to the middle. So that causes pretty big error. So there's an optimal point which can be analytically solved. And using this approach, like ResNet, MobileNet, and BERT, they can have a decent accuracy even aggressively quantizing them to only 4 bits, which is pretty impressive. Hello, folks. Welcome back. So we talk about the dynamic range clipping and rounding. And now let's talk about the next chapter about okay, now let's continue to talk about quantization-aware training. So usually, if you directly quantize a model, the accuracy is going to drop, right? So we want to fine-tune the model to recover the loss of accuracy with quantization-aware training. So to minimize the loss of accuracy, especially when we are aggressively quantizing them to very low precision, like 4 bits, fine-tuning is very necessary. In this example, we quantize them to only 2 bits by using the k-means quantization. This is the index, this is the centroid. We can back propagate to get the gradient and group them together and put the weight gradient with the same color corresponding to each group. And then reduce them and then multiply by the learning rate subtracted from the original centroid. So that's one round of stochastic gradient descent. And let's take a deeper look at a computation graph. This is layer m minus 1. This is layer n. This is layer f plus 1. And this is the forward in black. And the purple is in the backward. And for this particular layer n, we have the floating point copy. Okay, so the full precision copy of the weight is always maintained throughout the training, no matter if it's k-means or if it is normal linear quantization. Okay, and that is needed because we want to accumulate those small errors during quantization. Although at this iteration, say a number is 0, but say you went through 5 iterations, each iteration the gradient is 0.1. So after 5 iterations, this weight becomes 0.5, and it'll be rounded to 1. So that's why it's important to keep a floating point weight in the back during training to accumulate these subtle changes. Accumulating many subtle changes might lead to changing the actual quantization bucket. So once the model is trained, we no longer need this floating point value in the back, and we can directly quantize it and use the quantized value at runtime.
Would it be possible to be a little bit more concrete on what the actual check is to see whether errors have accumulated? So are we checking what output the quantized weights produce versus what output the original floating point weights produce on the same X? And if that differs too much, like you said, errors might accumulate. What's the actual check that we're doing to see whether errors have accumulated and how would we
Not error about accumulating, but the changes are accumulating. Say every time, for example, currently the weight is 0, and the gradient times the learning rate is only 0.1. Then after 1 iteration, if you don't keep the floating point weight, 0.1 will be rounded to 0. So next time you always also start with 0. You lost it. Although it seems small, but after 5 iterations, each one is 0.1. After 5 iterations, you can 0.5. Now it will be rounded to 1. So that's why it's important to keep small changes. It's similar to every day you learn a little bit, but after like a period of time, you get a pretty subtle, pretty big change.
So you actually want the small changes.
You want the small changes.
It's not that errors are accumulating, correctness is accumulating.
Correctness accumulate, right? Point. So that's the weight. How about the activation? So we want to insert this quantization node, this quantization computing node after layer n. Over time, you want to turn it into a quantized value before feeding to layer n plus 1. Okay, so here we call this scheme simulated or fake quantization. Why is it called fake quantization? Because we are still maintaining the floating point weight in the back during training. And also for all the data path here is still FP16 or FP32. Because the value is, for example, 1, but it's still represented 1, 2, 3 are still represented using floating point number, so that when you're doing back propagation, you can capture those small subtle changes. Here, make sure we have this activation quantization computing node to ensure that the split value weights and activations are in the boundaries. The boundary here before you pass to the next layer. So let's see a concrete example.
If the like full precise weights are still used for training, how would this be? You're using credit. How would this be different from just calculating everything on stage?
Right, if full precision weights are used, what is missing? So we will remove this part. Then we are directly using the full precision weight to multiply with the input.
I don't understand the first bullet that goes with on the used. In the training process is the quantization being used directly. So I thought the first bullet says that's not.
So this is the full precision way to maintain in the back, and this is the quantization function. Say this is 1.2. After quantization, here it becomes 1. So actually 1 is passed to the network during inference time. And if you get a gradient, which is 0.1, you don't add it to 1, but you add it to 1.2.
Why? You're saying that's only for inference. Why not just train the model normally and do what we did last slide here, where we quantize the weights after? Like, I guess I'm having a hard time understanding if the weights are not being used during training. What's the benefit? It's just doing it one step.
So training has forward and backward, right? So this is first of all, the model has already converged. You quantize it, and then you want to fine tune it to recover the accuracy. And during fine tuning, you have the forward phase and also the backward phase. During the forward phase, for this FP32 weight, this is FP32 representation, but actually this might already be quantized to like an integer value, like 2.0, right? And then you are using the quantization function to turn it into a integer value. Whatever gradient you get here, you accumulate it over this 2.0. So it may become 2.1, 2.3, and so on.
If you could explain to me why this is better than just doing than just using the weights, like what, like is the idea that there's some kind of like I don't know, like interaction between like.
Yeah, let's give an example, right? So say you have previously, just imagine you have only one weight. Okay, so previously the weight would be like 2.4. Okay? And after PTQ post-training quantization, which we learned previously, the value is quantized to 2. Okay? And we want to capture those small changes. Say the gradient is 0.1. Now you want to capture this 0.1. So after one iteration, this weight becomes 2.1. If you don't have this floating 32 copy, but always use integer copy, you're never going to capture this 0.1. It's going to be run into 2 again. But if you have this 0.1, what do you do in the forward time? You quantize this value again to 2. You forward, you get a gradient, maybe you get another gradient, which is 0.1. Okay, and what do you do here? You add it to the FP32 copy in the back. So that becomes 2.2. At forward time again, you quantize this 2.2 to 2. You forward again, you may get another gradient, which is 0.1. So you update FP32 copy in the back, you get 2.3. After a while, it may become 2.5. Say after 5 iterations. But now you want to do the quantization, that becomes 3. So that finally updated this way.
Right, I understand that, but what is the advantage of taking the gradient at the quantized points instead of at the like, continuous point? Like, why is that gradient better? I guess.
you mean why you want to do the forward using the quantized value?
Yeah, what do you think?
Right.
Doing that in this,
That simulates using the integer to run the inference and what is the loss, and use that loss to calculate the gradient. So you use this tool, which is if you deploy it on hardware, you're going to use this value to run inference and calculate the loss. You're not going to use 2.2 because the actual deployment time, we are using the quantized value.
If true, the ideal values between the integer, we used to get fluctuation back and forth.
It's possible. It's indeed. Say the gradient is not 0.1, but sometimes it's minus 0.1. It's highly possible.
Because then once we change the next integer, maybe that's too far, and suddenly the gradient is the same.
We'll put it back.
Backwards.
Highly possible.
For a deeper network, is that going to accumulate cause instability?
We are going to visit that during on-device training. But so far, this is the method people widely used for fine-tuning a quantized model. The detailed dynamics, maybe you can craft some handcrafted example. That could be a very interesting final product to explore this.
With this, I just out of curiosity, nobody is like training like a model from the start via quantized.
There are people training from scratch a quantized model, but that one is roughly in 2016. That is very widely used, but nowadays people train floating point always to converge, and then quantize it using PTQ and then QAT to fine tune. That's the standard like flow in industry.
That makes more sense than starting.
Floating point. Right. All right, so let's move on. Here, let's review some notations. We call this matrix to be QW, since this is the original weight, this is the quantized weight. And after this reconstruction, by subtracting the 0 point multiplied with the scaling factor, we call this QW. So you see here the difference in notation. This can be represented in integer. This is still represented in floating point. So here we are going to have QW and QY. They are represented actually by floating point number. But that already incorporated the impact of quantization. But just here we have subtracted the bias and multiplied with the scaling factor to let the neural network know, oh, I have done something to the model. So this is the model this is the way you're going to use for inference, not this one, although they are pretty similar. But here we're not using this because these two, the absolute L2 norm difference is actually quite big. We are using this one after this quantization node for both the weight and the activation. Okay, so how should the gradients back propagate through the simulated is fake quantization? If you have a chain rule, partial QW is partial W is actually 0 because this is the quantization, this is the W, this is the QW, it's flat everywhere, but it jumps. So the GW partial loss over partial W equals to partial loss over partial QW and partial QW over partial W. Since this one, the gradient is 0 everywhere, except for abrupt changes. The gradient is not going to flow. So a very commonly used method is to use this STE, the straight through estimator, assuming the gradient is 1 everywhere. So in that case, we can directly use the partial loss over partial QW to calculate the GW. So here, this is the partial loss over partial GW. Directly use that to update W. Okay, similarly, for the Y, we also use this straight through estimator to directly pass the gradient through this block assuming here is just one, the gradient multiplier is one, here is one here. So we can directly flow the gradient in this way and also flow the gradient in this way.
Maybe a silly question. So the previous slide that we were discussing, 5 minutes ago, I thought I understood it fully, but now I'm a little bit confused because if we're keeping the weights, then and we're using the floating point weights for backdrop, shouldn't we not have a problem with taking gradients and propagating gradients?
If you are using the floating point weight in the back.
Right.
In the what is the question exactly?
So we only take gradients when we're doing the backward pass, right? So if we're using the floating point weights when doing the backward pass, there's no quantization. So why is there this problem? Why is there this latter problem with the gradient being zero almost everywhere?
Oh, we are not treating it as this way, but ignore that part. So in here, we are directly passing the gradient to here. So you treat it as a floating point. So you don't have that problem. So make sure to distinguish between this QW and also this QW. This is in the integer space. It ranges from -128 to +127. But here the weights are usually small, ranges from like -2.5 to +2.12, for example. They're in two different spaces, and we are passing the gradient to this space. And assuming the gradient between this one is what?
But isn't it, if we're using the floating point values, there's no quantization, right? So shouldn't it just be the LDW, partial L, partial W?
Right, that's exactly what we treated. We treat it as if there's no such conversion in the middle, but directly use whatever gradient flowing back to the
I
to the
see.
weights.
So this is if we weren't doing
Yes,
if we weren't keeping the floating points, then this would be a problem, but it's not.
right. So let's see, after quantization-aware training, the accuracy can be improved a lot. For per tensor, it's more apparent from 0.1 accuracy to 70% accuracy. And for per channel, the original accuracy, you can imagine per channel quantization is better than per tensor quantization. But after this fine-tuning quantization-aware training, the accuracy improved from 59 to 70.7. And as a result, after quantization QAT, the accuracy is pretty much roughly catched up with the original accuracy. Okay, so we want to go one step further to continue compressed model using binary and ternary weights and using bitwise operations. And let's see, how does binary and ternary quantization works? Can we push the quantization precision to only 1 bit? So let's review. This is a normal case, 32-bit weight, 32-bit activation. I multiply them together. Both the input and the weight are real numbers, IP32 or IP16 representation. We can change the weight to make it binary. Okay, so just look at the sign. If it is positive, then it's 1. If it is negative, then it's -1. In that case, the memory is 32 times smaller, and the computation is 2 times smaller, since one of the operand is either +1 or -1. So you don't have to do any multiplication, just only addition. We can do either deterministic binarization like what we did just now. Just look at the sign. If it's larger than 0, it's positive. If it is smaller than 0, then it's negative. We can also do stochastic binarization. Okay, so it's +1 with probability p equal to sigma r. Okay, what is sigma? So this is a step function. If it is below -1, it's always 0. If it's above 1, it's always 1. In the middle, that's linear. So if you're here, 100% you're 1. If you're here, you're 100% you're 0. In the middle, you have the linear interpolation between 1 and 0 can be rounded either to 1, positive 1 or minus 1. So this is our familiar weight matrix. We can binarize them by just look at the sign or using the stochastic rounding. The difference is actually pretty big. So the accuracy drop is very high. You can imagine changing them to only 1 bit. How can we do better here? We have this scaling factor, right? So we can use this scaling factor, try to align the average of the absolute value, right? So here we are multiply that with a scaling factor 1.05. And how do we calculate that scaling factor? So the scaling factor alpha equal to the average of the absolute value. You just sum up all the absolute value and divided by 16. So we use that. We use that 1/16 our norm to multiply with the alpha. And we can see after that, the accuracy is actually improved a little bit. So actually, this alpha is quite crucial during binarization of neural nets. Can we do even more aggressively by not only quantizing the weight, but also the activation to only 1 bit? So in this case, we have the weight activation, etc. Everything is -2. So can we have what is the analogy between this binary multiplication versus XOR? You see 1 times 1 is 1, 1 times -1 is -1, etc. But if you're doing XOR, if they are the same, it's 1. If they are different, 1, 0, or 0, 1, then it's 0. If they are the same, 0, 0, it's a 1. Did you find some similarity between the result here versus the result there? Try to see the color. We can assume everything is minus 1, right? If the XOR result is a 1, we can add 2 to the base. If the base everywhere -1, -1, -1. If the XOR value is 1, then we actually add 2. So that's exactly here. The original result XOR 1 is 1, 0, XOR 1 is 0, etc. The relationship is assume all the result is -1. Then if you sum them up together, it's -4. And how many non-zeros you have here? Okay. Whenever you have a non-zero in the XOR, you add 2. So comparing here, comparing here and here, actually you are adding 2 on top of -1. Assuming if everything is -1, if suddenly you have a 1 here, and you're adding 2. So you just count the number of non-zeros, which you have 1 non-zero, you multiply it by 2 and add it to the base, which is assuming everything is -1. You know, 4 of them, then it's -4. And you count the number of non-zeros in the XOR, you have 1 of them, you multiply by 2, that gives you the same result when you are calculating using the binary arithmetic. Give you 1 minute to think about it. Make sure you're convinced. We can calculate the sum of several XORs in this way. Right? If the XOR is 0, it's -1. Only if the XOR is 1, then it's +1. So the difference is 2. That's why we are counting the number of non-zeros and then multiply by 2, added to the number where assuming everything is -1. So that is the basic equation, calculating it using the external equation, multiplied by 2 and added to -n, assuming everything is -1. So plug it in, we can do the math here. And then this summation is mapping, can be mapped to a very efficient hardware operation called pop count. Basically, given an array of numbers and return the number of ones in this array. That's called pop count. So put it here. The arithmetic of two binary vectors to do the dot product can be simplified by -n plus pop count x nor left shifted by 1, meaning multiplied by 2. And everything here is very hardware efficient operations. Pop count, counting the number of ones, shift, addition, those are all very cheap operations. There is no multiplication. And using that, we can calculate this dot product. 1 minus 1, 1 minus 1 dot product with this value. We can basically use the equation, turn it into an XNOR operation. XNOR operation is very easy to calculate in hardware. This is the XNOR operation. We run the top count, 1 9 zeros. This is 1 multiplied by 1, multiplied by 2, and then multiply with the base, assuming everything is -1 and 4 of them. That's why here is -4. You get the result -2. Okay, so let's see the accuracy. The actual net is slightly better than the BN binary neural net. Almost still cannot catch up with the binary weight only. Binary weight only can pretty much recover the accuracy. But XNOR net is giving a pretty big improvement on top of the binarized neural network with the without the scaling factors. We can go another approach to introduce a 0 in the weight. Okay, since during pruning lecture we find after 0 is a very important value, we can skip it. Since 0 multiplied anything is 0. But here we need to use 2 bits to represent them. Actually weights in one slot. So we can either round it by using a fixed threshold. If the value is larger than threshold, it's positive RT. If it is smaller than this threshold, it's negative RT. If it is in the middle, it's 0. And this threshold can have a heuristic like 0.7, the expectation. And why is 0.7 is pretty much just heuristic. Given this matrix, we can calculate 0.7 times the average absolute value is getting the threshold of 0.73. Then we can compare with that. If it's larger than 0.73, it's a 1. Smaller than minus 0.73, it's -1. In between, that will be 0. And again, if I have the scaling factor, the average value of those non-zeros, we can find using this ternary weight net, we can have a higher accuracy compared with the binary weight net. And here the tricky part is, why do we have this RT and this strange heuristic 0.7? Can we have a learnable solution? So here we can indeed have this learnable solution. We can have the positive value and negative value to be different. And in this way, we can further improve the accuracy a little bit to push the frontier for ternary weight, train the ternary quantization. So put them together, we covered both 8-bit, 4-bit, and even the binary and ternary quantization. And the most important thing to keep in mind is that computation is cheap. Memory reference is expensive. So as you go deeper and deeper, quantize the model, you have diminishing return, because from 8-bit to 2-bit, you get 4 times less memory. But how much reduction of compute do we have? 16 times. So computing is quadratic with the number of bits. So to reduce aggressively reducing the precision is giving you linear return for the memory, but quadratic return on the compute saving. Since compute is more expensive, you get diminishing return as you go deeper and deeper, quantize the model. And so far we find 4-bit is pretty much a sweet spot. All right, just like different layer of pruning, they have different sensitivity. Similarly for quantization, that is always also the case. So we will introduce mixed precision quantization to allocate a different number of precisions for different layer. Okay, so this is the weight, this is the activation. Now we are using 8-bit to represent different layers, very homogeneous, 8-bit everywhere. For mixed precision quantization is saying some of the layers are less sensitive to quantization, then we can use more aggressive quantization. Some of the layers are very sensitive to quantization, so we'd better use less aggressive quantization, and so on. So this is a pretty big design space. 8 choices for the weight, assuming 1 to 8 bits. 8 bit for activations, also assuming 1 to 8 bits. 16 choices for each layer. If n layers, do you have 16 to the 64 to the power of n number of choices? That's pretty huge. So again, we use this RL method of actor critique, and also have the hardware mapping, how to map this mixed precision model onto the hardware, collect the direct feedback, including the latency and also the energy to generate the state and also the award. And then the critic is going to propose another action in the next iteration. And as a result, compared with uniformly reducing the precision, this hardware-aware quantization by using mixed precision can get a better trade-off between the latency versus the accuracy, just like pruning. For other metrics like model size, latency, and also the energy, this mixed precision quantization can consistently outperform this uniform quantization. But only catch is here is that requires more engineering effort. You have to deal with the compiler, the tool chain to effectively exploit this mixed precision quantization, which is quite non-trivial. So in practice, in industry, people use very coarse-grained decision. For example, only for all the comp layer, you use 1 precision. For all the FC layer, you use 1 precision. To balance between the engineering complexity versus the performance. Very interestingly, on the edge device and the cloud device, this RO agent find different quantization schemes. Like for the edge, it allocated fewer bits for the depth-wise layer. Maybe due to the depth-wise layer is very memory bounded, it has very little compute. So it allocated fewer bits for that. And point-wise layer, this 1-by-1 convolution, allocated more bits. All right, so in summary of today's lecture, we introduced 2 very important concepts and followed by 2 fun concepts, but not that important. Most important probably is the post-training quantization and also the quantization where training, we introduced the different quantization granularities per tensor, per vector, per channel, and also group quantization, especially group quantization. You want to have a deep understanding for that, since that's the method very widely used for large language model quantization. Below 4 bits, we have to use group quantization with multiple levels of scaling factor. And also how to determine the dynamic range, how to clip it, how to round it. Followed by this quantization-aware training. Remember this straight-through STE, straight-through loss. You always have FP32 copy in the back when you are doing quantization-aware training. Following this rule, you want to always keep this floating point value in the hope that after a while, the bucket quantization bucket is going to change. Binary and ternary quantization not quite widely used in industry these days because you have diminishing return going fewer than 4 bits. But this pop count and XNOR is pretty interesting idea. People use it to make a startup. Very interesting. Acquired by Apple. So very interesting technique. And also mixed precision quantization to further exploit all the redundancies in different layers. So when you have different layers like like transformer layer, convolution layer, FC layer, you may consider using this technique. Here are some references for today, and that's all for today's lecture. Thank you.